Good morning, good afternoon, and good night. My name is Sarah, and welcome to my podcast today. If I were to give my podcast a name, it would be called What the Hell is Sarah Up To instead of studying, and I would never guess what I'd be up to. But today, I'm going to be talking to you through quantum physics, Schrodinger's cat, and real-life multiverses. Don't be scared, I'll keep it easy. But it's gonna be a wild ride. One day, a physicist named Niels Bohr published a paper that rocked the realms of modern physics. Some math in the paper said one crazy thing. Very small particles, and I mean very, very, very small particles, like electrons and protons, 电子跟光子, have crazy properties. Big stuff, like us humans, rocks, your dog, basically everything you see, can only be in one place at one time. But, according to Bohr's math, the small particles, they can move on two paths at once. This is called superposition. However, the second you look at that particle and take a measurement, then boom, the thing now can only move down one path. The superposition collapses instantly. Do you understand what I said? If you didn't, let me try to explain that again. Very, very small particles can go down two paths at once until you look at it. Then it only goes down one. If you still don't understand how the hell that works, do not worry. You are not stupid. A ton, and I mean a ton of people didn't understand. Not even the brightest minds in the world understood. Einstein didn't understand it. Him and another physicist wrote an entire paper arguing against Bohr, where Einstein critiqued how flawed Bohr's paper is, allowing, quote, spooky action at a distance, unquote. I'm going to talk about this later today. Another brilliant mind that called BS was physicist Edwin Schrodinger. Schrodinger actually wrote some of the math that Bohr used in his paper, but Schrodinger did not agree to that paper at all. He thought it was ridiculous. So much so that he felt the need to prove just how ridiculous it is using an imaginary cat. The kitty that became the main character in his infamous thought experiment, Schrodinger's cat. Now, I don't want to complicate things, so just know that my explanation of this will be heavily oversimplified. But this is the essence of it. Imagine you have a box with a cat and poison inside. The poison is controlled by a small particle. If the particle goes down path A, the cat lives. But if the particle goes down path B, the cat takes the poison and dies. Now, remember what Bohr said in his paper? Tiny particles can go down two paths at once until you look at it. So, before you open the box, the particle can go down path A and B at the same time. The cat can be both dead and alive at the same time. But the second you open the box and look at the particle, it only goes down one path. So the cat becomes only dead or alive. How the hell can a feline in a box be dead and alive at the same time and then become dead or alive just because you opened the box? That didn't make any sense. it doesn't make any sense. It didn't make sense to normal people. It didn't make sense to geniuses. Not even Bohr's team can give an adequate explanation to how the math worked. But here's the most mind-contorting part of the story. Bohr's math worked. It worked perfectly. The math didn't make any sense, and it actually broke the rules of math at certain parts, but it made predictions that perfectly matched experimental results. No one knew how the math worked. Not even the researchers of the sting knew how the math worked. But it worked. Perfectly. It drove people crazy. So, here comes the million-dollar question. How does the math work? Why does it work? There's gotta be a reason to this, right? This is one of the most heavily debated topics in physics to this day. Many scientists tried to give possible reasons. There are like 15 interpretations on the Wikipedia page for this. But in reality, so far, no one knows for sure why the math works. Today, I'm just going to talk about the biggest interpretations, which are complete theories that try to explain this, and the important concepts within them. Get ready, because this is where things get wild. And as we progress, they only get wilder. The first interpretation was posed by Bohr's team themselves. And it is very simple. It goes like this. Don't ask me why it works. Trust the math. That's it. That's the whole thing. The Copenhagen interpretation just states that the math looks crazy. The whole thing feels wrong as hell. But it works perfectly. And that's reality. So accept it. Just on a side note, that's a pretty good life philosophy to incorporate. That would save me so much time overthinking. But, as you can tell, not many people liked this explanation. The second group of scientists tried to bridge the gap with a special idea. Remember again, in Bohr's paper, he stated that a particle can go down two paths at once, but can only go down one once you look at it. So the problem here is, why does just looking at it change the state of the particle almost immediately? Here's the idea they proposed. Normally, our particle can go down two paths at once. However, when you look at it, you would do some things and add a lot of new stuff that mess up the particle. When you take a measurement, maybe you turned on the light of the microscope and introduced photons. When you opened the box in the cat experiment, you might have let in sunlight, or dust, or LED light, or things on you. Now, to a human, sunlight and dust probably isn't that big of a deal. But when our particles are some of the tiniest things in the universe, they become a huge deal. These scientists said, all these new things you added will disturb the particle to the point where you only see it go down one path instead of two. This idea is called decoherence. Now, there's an interesting concept in decoherence called quantum entanglement. 如果听到这里的朋友，首先你真的很厉害。第二 ，quantum entanglement 就是大家一直听到的量子纠缠。When you look at your particle and it only goes down one path, that's because the particle became entangled to some new particles, and hence it became entangled to the path you see. But here's the strange yet fascinating thing about entanglement. As long as your particles are alone and not stuck to something, any two particles can become entangled at any distance. Now, I don't know what you think about this concept. Einstein found this absurd. This is the spooky action at a distance he mentioned in the very beginning of today's episode. However, if you ask me, I think that's scientifically romantic. Let's say you and your partner are far, far away. Now, like I said, the particles have to be isolated. So this won't work for the things that are still stuck on you. But the second your particles float out and his or her particles float out, your two particles can become entangled no matter how far you are. You and your lover can be on opposite ends of the universe, but your particles can still become entangled with each other. This theory brings me to my last and probably craziest interpretation I'd like to talk about today. The third group of scientists extended on the last theory. They agreed that when you look at it, you add new things and disturb your particle. But that's kind of where the similarities end. According to this group of scientists, the second you look at your particle, the second you open the cat's box, listen carefully, the universe splits. On one timeline, the particle goes down path A. It becomes entangled with path A. But on the other timeline, the other universe, the particle is entangled with path B. However, the more new things that float in, the more entangled they become with their own path. And the further these two universes divide. That's why you only see the particle go down one path. You only get to see one branch. You will never see the other timeline. The many worlds interpretation states that you only see the particle go down one path because you only get to see one universe at once. And as you could already tell, this implies an existence of alternate universes. Tons of alternate universes. Every single time a quantum event happens, every time you look at a particle and measure it, you're dividing the universe. Time is no longer a single axis. It is a massive tree of branches. And on each timeline lives a different version of you. Maybe in one branch, you're an astronaut. In another branch, you're Taylor Swift. In a third branch, you're living on another planet. And all these versions of you coexist. They live with you right here, right now. You just can't see them because they're on different timelines. This interpretation gives me so much hope because, to me, this means that nothing is impossible. When you face a challenge and you think, oh God, I don't think I can get over this, perhaps in a different universe, you've already conquered that challenge. Maybe in another universe, you already became the person you want to be right now. The dream version of yourself. And these versions of you live with you. You just can't see them. Out there, in those different universes, you, yourself, you have already proved that you can be anything. And all these versions are reality. They live alongside you. You can be anything you want to be. Allow me to remind you that all these concepts I mentioned are actual explanations in modern physics. Massive teams of researchers wrote complex math to prove that you can always be connected to your lover, and perhaps parallel universes are real. This corner of science has gotten so theoretical, it sounds more like religion. However, the ambiguity of this is precisely what makes it so fascinating. This is a corner of our world that not even the smartest humans understand completely, so we can only wonder. So the next time you see a cat in a box, you receive a text from your long-distance partner, or ponder about your life, your dreams, and your future, you can come back and marvel at what science has to say about it. Thank you for listening.